Okay, here we are, 8-5, day 2. Still finding volumes of solids, but this time the shape is not going to be a cylinder. So we're going to revolve a region bounded between two curves. So let's say we had something. Here's function 1. And here's function 2. And we're going to take this region in between here and say revolve it around the x-axis. Well, if you think about it, we're taking these two little rectangular piece here, and if I spin this around, I'll try and draw it again. And here's the bottom. Oh, up here, sorry. Just so you know, I'm doing a terrible job at this. Well, anyway, you get this solid shape right here. Try and shade it in. So there's this opening in the middle here. What you're creating are washers. If you think, nut bolt washer. So the difference is, yesterday when we did the cylinders, our rectangle went all the way to the axis that we were revolving around. Now we've got this gap between our function and the axis, creating this hole in the middle. And I'll show you the book picture. It's a little bit better than mine, obviously. It's right here. So it's the two curves, taking the region in between and revolving around. See the washers here? The opening in the middle? So what we're actually going to be doing to find the volume of that washer, we're going to be doing, pretend that it's a solid cylinder, pretend the hole wasn't here, so a cylinder, and then minus the volume of the middle piece, which is also a cylinder. So it's the outside cylinder minus the inside cylinder, which will leave us with the part that's actually solid here. So the volume of a washer is going to be the volume of the outside cylinder minus the volume of the inside cylinder. So the volume of the outside cylinder, just like if that rectangle went all the way here, the radius of the cylinder would be defined by this outside function. So it would be pi, we'll call that R1, radius 1 squared, times the height. And the height is the thickness of the, let me go here. So the R1 goes from your axis you're revolving around all the way to the farthest function. That's R1. The height is just your thickness here, your dx. Okay? The inside cylinder, it's still pi r squared, but now we'll call it R2 because it's not the same radius. This radius goes from here to the closest function. That's your R2. And the height, it's still that same width across, so it's the same height. Now if you think about this as two baskets in factoring, they both have a pi in common and the same height. So if we factor that out, it kind of condenses our formula that we're going to be using for the volume of a washer. So it's pi h, that we're taking out, R1 squared minus R2 squared. So our radius length is coming from our equation. And I think that's that's all you need to know. So the volume then to integrate, so the volume of a washer will be the integral from A to B of pi times r1 squared minus r2 squared, and our height is dx, or dy. Let's see what I want to put there. I'm going to go h. Call it h underneath. Because depending on which way our rectangles are going, this could be a dx or a dy. So I think I'm going to leave that. No, I'm going to go one more time. So in terms of x's, your rectangle is perpendicular to the x-axis. You'll have an a to b that are both x's, pi r1 squared minus r2 squared. And if these are x's, that'll be top minus bottom. And then dx. If your rectangles are perpendicular to the y-axis, we're going to have an a to a b, but they're going to be y values, y1 and y2, pi r1 squared minus r2 squared. This will be right minus left. And I'll have a dy on the end. Oops, sorry for all that. Oh, look at that. Sorry. I'll let you catch back up. And that means my equation, my radius in here is also going to be in terms of y. So I have y boundaries, dy, y's inside. That's when it's perpendicular to the y-axis. Perpendicular to the x boundaries, x equations, x expressions for the radius, and a dx on the end. So everything's got to match. All right, let's try a couple. Once you've got the formulas, just like we did yesterday. So, and today's homework is going to have both cylinders from yesterday and washers from today. So, example 1. Find the volume of the region bounded by y equals e to the point 2x and y equals 0.5x plus 1 if that region is revolved around the x-axis. Okay, graphing both of those. Clear, y equals e raised to the 0.2x and 0.5x plus 1 is linear. There's my e. There's my linear function. I can see the line is above the e function. So rough sketch. Okay, when I draw my rectangle, I have to touch each function. So I know I'm going to draw them top to bottom here. And I'm revolving around the x-axis. So I know I want x boundaries. Here's my A. Here's my B on the x-axis. I'm going to find that first. So, and I do that by setting the equations equal. So if I set 0.5x plus 1 equal to e to the 0.2x, this is not something I can solve algebraically very well. So I'm just going to go to my intersect on here. Intersect. It's on y1 right now. Enter. Jump to y2. Enter. Those are the only two functions in there. The guess, it's very close to it. I'm just going to hit enter. And it is 0, 1. So my a value is 0. Now I'm going to go out and find this intersection. Start the whole process over. Intersect. It's on y1. Hit enter. y2, enter. I'm going to slide out there by using my arrow to the right. And the x value is 8.09. Did not want the y values. Okay, so now I've got to determine my R1 because I've got this vertical rectangle. It's top minus bottom. So my R1 is the linear function, because that's on the top. That's my 0.5x plus 1. And I want it in terms of x, because I'm going to have x boundaries. R2 is the bottom one. That's my e to the 0.2x. Just defining those. If I had to rearrange them like the next one, I would have, but I'm good to go there. So now I'm ready to set up my integral. So the volume is equal to the integral from 0 to 8.09. This is a washer. So the washer formula is pi times R1 squared. So that is 0.5x to the 0.1 minus R2 squared. That's e to the 0.2x squared. And then my height is dx. The height is the width of my rectangle. Okay. Because I've got to integrate these, and remember this is the first power out here, so I can just distribute the pi to each one of these. And I am going to write them as two separate integrals because this one's an inside to a power, this one's an e. They're going to have different rules. So I'm going to take the time to rewrite this first one. The integral from 0 to 8.09 pi 0.5x plus 1 squared dx. And I'll subtract 0 to 8.09. The pi is with this one also, times e, and I think I will take the time to multiply this together because I can. Remember, a power raised to a power you multiply, that's going to give me 0.4x dx. Okay, now integrating. So I just do this problem all by itself. The pi I'm just going to carry along. I have an inside to a power, so I have to have the derivative of the inside attached to the dx before I can integrate. So the inside derivative is 0.5, so I need a point, that's 1/2. Multiplying by the reciprocal, I'm going to multiply by 2. So I'll have a 2 pi out in front. Then I will add 1 to the exponent and multiply by the reciprocal there, 1/3. So I'll make this 2/3 pi. Minus, and now this one, the e to the u, remember you have to have the derivative of the u attached to the dx, and then it just integrates to itself. The derivative here is a 0.4, or that's 4/10. I'll multiply by 10/4. That's 5/2. So I will carry along the 5/2 pi, and now this integrates to itself. And then I can evaluate both of them from 0 to 8.09. So at this point, I would use the y equals in the table for this. And don't automatically assume when you plug in 0, you get 0, because that's not the case here. So if I go to y equals, clear out what I've got, type in this ugliness here, 2/3 pi 0.5x plus 1 cubed